Okay, someone is asking how do you access the Julia file they made yesterday?
Uh, yeah, just give me 1 second.
Yeah.
Yeah, I think I put it up in the Discord channel. Might have been
So no, so the Julia file that they made on their system, they want to access that. How to do that?
access in what sense? What exactly do you mean?
Like uh, they want to use that file again, right? For animating. How would they open
Ah,
that?
right, okay. If you have it on your system, you can open it via the file browser in Pluto itself. Uh, I could show that. Let's launch Julia. Uh, right, so in Pluto itself, there'll be a field where you can fill in the file path. So wherever you saved it, even if you didn't save it, I think it will give it some temporary name and then you can access it by that.
Also, you started recording, right, Akshay?
Yep, yep.
Fine.
Just in case though, if there's anyone else who can also record, that would be good in case I mess something up. So you see the reason sections here. So it just gives its own name in case you did not actually save it. So it's still fine. You can just pick it here, whatever the last file you opened. I have saved it as the simple pendulum. So for saving that file, I guess in the top, okay, let this load. I should- so you see that there's a save notebook here, right? So you can just enter your own path and file name or whatever, and then press enter. It'll just get saved. You can actually access it outside Pluto also, because Pluto doesn't have its own file format. It's just a .jl file, so you can open it by any other text editor as well.
Right. Yeah.
So, right, this is where we left off yesterday. I guess like the last 15 minutes or so was kind of rushed up. So if something is not clear, you guys can ask right now. We could quickly go over what I've done, or was everything clear? Okay, I'll just quickly go through it anyways, in case. So what we started with was we created our own, like data type, which is a pendulum, and in it we included the abstract properties which we had decided will completely like specify what a pendulum is, namely two dynamical variables, that is theta and omega, and some passive properties which are not going to change during the time evolution of the pendulum. And in the last 5 minutes or so, I quickly added some a new field called trajectory. So the intention of this trajectory is to store all the previous angles that the pendulum has gone through. So that way I have like a history of the entire path, right? So that's why I called it trajectory. So this way, in one go, I'll have uh, all the angles that my pendulum has gone through, so I can plot it more easily because that's where we left off last time, just before plotting, because our simulation itself is actually done. Uh, and to do the simulation, we actually broke down the updating process into like three functions. Namely, the first one, which gives you the angular acceleration for a given angular position of the pendulum, and then an update function wherein we actually do the update. This is what we derived yesterday, by doing the Taylor expansion and truncating it at the first order, right? So, and after calculating like the new angular velocity and the new angular position, we push the new angular position into the trajectory array. So this push bank basically does an equivalent operation to appending. So every time I update the position, I just throw it into trajectory, so it'll keep track of the entire history. Uh, right. So And finally, this just updates for a single time step. That is a uh, the time elapsed is a single delta t, which is like one discrete unit in our time step. So to actually evolve the pendulum over a larger period of time, we create this evolve bang function, which takes the delta t and the number of iterations to go through, and it just loops through this update function those many number of times. So like the final time elapsed throughout the simulation would be number of iterations multiplied by the delta t. So those many seconds have elapsed, like in real time, I guess. So right, and I had also told that this bang or the exclamation mark at the end of function indicates that I'm actually changing the object itself. So what that means is I'm actually changing theta, omega, and also the trajectory, right? So the fields of my object itself is changing. So in that case, I put a bang at the end of the function. So what it indicates is that the function is mutating the objects. So changing the fields, right? That is called changing fields is what I call mutability. And if I cannot change the fields, then I call it immutability. So yeah. And right, is that all? So we just created an object and we have evolved it for like 10 steps. And that's where we left off, I guess. So any questions? Anything which was unclear at this part?
So as of now, you're not storing the angular velocities at individual time
I
steps,
have
are
not.
you?
I've only stored the position,
Okay, okay.
angle. Yeah. We could do that also. In fact, we could make this theta and omega here as an array directly. I could just remove this trajectory also. So instead, in this update function, instead of updating omega, I would do something like omega of I plus 1 equals object dot omega of I, that is like the previous time step or something like that, plus
Yeah,
this.
that
So,
would be nicer because then you have a history of
history
both,
of
and you can
everything,
like
right?
connect,
Right, right.
and you can connect them also. So then you have a nice, you have some interesting plots you can make when you know both.
Yes, exactly. I didn't want to do that because you guys can try them, but more or
So
less, yeah, it's not that hard to. So in essence, this trajectory variable here is redundant. So I just quickly passed it together to plot it. But yes, ideally you would make these also as vector of load and evolve it based on that. Take the previous element in your array as the like a seed to find the next time step. I mean next angle for the next time step. Right. So yeah, you guys can try that. That will also work. And uh, okay, yeah. So uh, should be good. Okay, so I've run it 30 times. I mean, I ran this command 3 times, I guess. So there are like 31 points here. Okay, so I hope that part was clear. So we'll continue from there. I wanted to tell a few more things though. Let me remember. Uh, there's one thing. The one thing in Julia functions. We've defined a function like this, right? This is like a typical function definition in any language. There's actually a more convenient way. I'll define the same get alpha function, but in a more nicer way, which is just like get alpha. Uh, Same thing. Put the arguments with the types and equals minus 9.8, and I can directly write equal to whatever this thing is. Since it's a single line function, I can quite literally write it in a single line, and this is still valid. I can just remove this. So this works perfectly fine. It just returns whatever I wrote in the equal to side. So this is more like reminiscent of math, right? I could write something f of x equals x squared, and this is actually a perfectly valid function. It works fine, right? So if it's like a single line function, it's nicer to write it this way. You can quickly just see what it does instead of doing begin end or all of that. So I'll drop that back. Okay, that was one thing. And secondly, Okay. Would I teach that? Maybe not, maybe later. Okay. We'll just continue from it. We'll now go towards, actually visualizing, plotting, and trying to animate this trajectory. So, okay, let's start with, basic plotting in Julia. So for that, we use this plots package. The basic function is just plot, and the first argument generally is like a list of x values. So I would give something like 1 to 15. This is the range which we discussed yesterday. 1 to 15 maybe. And what will I give for y? I think I can actually just give a function for y. So if I define the function fx equals x square, I can just pass that function f, and I think it will plot a parabola. Let's see. So you see the first plot is taking a while because that's just how Julia works. It's taking,
So it's loading in the whole package now, okay? First.
yep, basically. So whenever I use this function now, if I use it here onwards for any other function, it should be fine. So I mean, see, now it's quicker. If I change the range and all, it's fine. Yeah. So maybe I can do minus 30 to 30, right? So this is one way. There are actually many ways you can invoke this plot function. One of which is providing an x range and just directly a function. So here there's an idea I'm using, that is the function itself is kind of like an object. So I've defined a function here, and I'm passing the function as an argument to this plot function. So and then it's like, okay, I'll map this range of values to what are the functional values and plot that. That's one way to do it. The second way is just plotting, giving the y values as well. So this would be a straight line because x and y are given the same range of values. So we'll be using this basically. We'll just plot x, a range of x values and range of y values. It doesn't have to be a range. It can be like a list also. So like 1, 2, and 3, 4 maybe. So that's the first two are the x values and the second two are, so it's like a coordinate pair of 1 comma 3 and 2 comma 4. So that's what this is equivalent to. Right, this is going to be a straight line. And there are also many additional properties you can pass to the plot function. For example, LW stands for line width. So I could set it to 2, maybe it should become equals. And there is another useful one called CDs type. So that's ST. And here I can pass something like scatter. Okay, if I do this, it should plot a scatter plot, right? So it's just 2 points. Um, I can actually plot multiple different series types. So if I give it the series types as a list, I could give scatter, and I think line is also another. So it plots both a scatter plot and a line. So you may be thinking, like, what is this new? I've introduced a new object here. It's like there's actually a colon, and then like the color changes. That means Pluto's identifying this as a new kind of object. So, and it is right, because what this is, it's called a symbol. It's called a symbol in Julia. If you guys have used Matplotlib in Python, it also has keywords like this. But there isn't the concept of symbols, but rather you do something like you just give a string saying scatter or something like that. So that's kind of an equivalent, but this is more capable, I guess. I'm not going to go into detail what symbols are, but it's really powerful stuff. You can use it to meta programming. So maybe look that up. It should be in the Julia documentation, I think. But yeah, this is how we specify, like attributes. These are called like plot attributes. So there's actually, if you go to the plots documentation, there's a whole list of attributes for the series, the plot, and axis. We'll see subplots sometime later. But yeah, so all of these are different options that you can change. So limits is another useful one. You can pass a tuple and get like set the access limits and all. Um, I guess grid would also be a useful one. I don't know what this is, right? Grid. So it plots a grid. You already have a grid. It's really transparent though. Okay.
Wait, so Akshay, how is it plotting the line? Is it plotting a line based on like best fit? क्या हो रहा है?
There are only 2 points to it. There's literally only a single line which can pass through it.
Yeah, no, but like that's still an object you're using, right? So let's say there were more points. What would it do then?
Oh, it just connects it. It just
So just
connects
put a no
pairwise.
point.
Acha, okay, okay.
So I can put 5 or 6, 7,
And that makes it uh,
maybe something better. So it just connects it pairwise.
fine, fine, fine. I see.
Same thing. I think it's a default behavior in like most plotting stuff. You can do smoothing stuff and pitch, but you'll have to do that manually. I don't think it does it for you.
Actually, if we add another square bracket list, so will it give a 3D plot or something? Like we use two square brackets lists
Okay,
Yeah,
okay.
instead of
that's what
two
I was
sets.
thinking.
No, no, I don't think so. No, this,
Oh,
this
okay.
I think for
It
3D
does, it
plots you'll have
does.
to use a different backend. I'm not sure. Let's see. Let's
No, GR also has. GR also has, and you can plot it in
Oh,
3D.
GR has. Okay.
Yeah, yeah.
How do
But
you
it's
do
just,
that?
huh?
How do you what's the syntax?
Just same thing. You put the set of Z values.
I just give a third lister. Oh,
Yeah, yeah. It'll take again a little time to
oh, that's
plot it.
nice.
Yeah,
I didn't know that.
Wow.
Cool.
but you can't. There's no. I mean, you can't move it around and stuff.
Right,
For
right.
that,
I'm
you'll
literally
need
trying to do
Plotly.
that. Can you use plot?
Yeah,
Right,
so
right. Yeah.
Plotly. Yeah,
There's plotly JS or something like that, I guess.
or you could just call Plotly and it'll still
What's the
work.
difference? I think one is for web embedding in web
Yeah,
application.
so Plotly.js, no, both are the same.
Okay.
Plotly.js, all it does is that the plotting and everything happens on your device, whereas Plotly sends it to a server and the server does it and then sends the result back to you.
Ah,
So, I mean, yeah, it doesn't matter if you're connected to the internet, but if you're not connected to the internet, then it does matter.
right, right. But okay, so plotly or
And
plotly JS,
Plotly,
you'll get interactive plots. So that's what you need to know.
so and the best part of Plotly is that it's already loaded into plots. So you just call Plotly the function,
Oh, I see.
and
Oh, can
it'll change the backend.
just
And,
plotly now.
yeah,
Okay.
so you can show that right now.
Plotly base has to be installed. Okay, I don't want to save it. It's fine.
No, yeah. But again, it'll take a little time because now you used a different backend.
Did it even plot? Okay, it has plot. Ah, that's cool. That's cool. Nice. So what we've done here is basically there's a concept of backend. Dhruva, can you maybe like tell what that means? What do you mean by
Yeah,
specific
so
back?
plots, the package plots doesn't actually plot anything. The way that it works is that the people who wrote plots, they realized that there are beautiful plotting libraries which each have their advantages and disadvantages. For example, in this case, what we had previously plotted, we used a backend known as GR, and that creates very fast plots and they look very nice, but the problem is that it does not have interactivity. So when you plot it in 3D, it kind of gets difficult to visualize exactly what's happening. uh, the flip side, so what plots could have done is gone ahead and written everything and tried to put everything into one package, but they felt instead of doing this, there are a lot of plotting libraries which you can. But the problem is, if I want to, let's say, switch from GR to, let's say, ggplot or gnuplot, some other plotting library, then I have to change syntax. So all that plots.jl does is that it provides a uniform interface such that without changing the code to plot, it it just uses a different backend. By default, they use the GR backend, but then let's say you want to plot a three-dimensional thing with interactivity, then you will simply switch to Plotly. Suppose you don't want this thing, you want instead very fast plots. Then there's something known as inspect dr. So there are different backends which have different advantages and disadvantages, and accordingly you can simply change the backend but not change anything in your code. So the plot will look different and it will perform differently, but the code that you've written remains the same, because the point of plotting is not to tell what you want to plot. You don't need to tell how to plot it, you just want to tell what to plot. That is the aim of the plots package. I'm done.
Hmm. Okay, that's cool. I didn't know you could plot 3D plots.
That said, yeah.
Hmm.
That said, that for today's thing, I think stay with GR because Plotly will get very slow for simulations.
Okay, okay, sure. Fine. So we have this. Let's try the myths that work. B minus 5, 5. Okay, it works. That's it. No, I don't think it works outside. Okay, now it works. Fine. So like a list of two values to X limbs and Y limbs. Fine. So I think that should be enough for us for today. Oh, also maybe color. Line color LC maybe. Okay. Line color. Not sure what the color for the markers are though. I'll check
Marker color.
for like M. C. Red maybe. Okay. Maybe. And then we're sorted, I guess. So that's about all we'll need. With that, let us try to plot the first pendulum.
Excuse me.
Yes.
Just one. Don't want to sidetrack, but in Python, can you like do both the scatter and line using the same like this is as such? I mean, like you're not wrong. There's some other scatter of whatever function and the
I
plot
think I think
function
you
for
can. I'm not sure
instance.
exactly how, but I think that
So in Matplotlib, you can do it. You have to send with the way that you change the color is by sending an R as a string, right? So there you can put a O and it will print it as it prints it as a scatter. So if you want both scatter and a line, then you need, I think, a dash O or something like that. It has some weird syntax which you can use.
right. I think
Right.
there is a similar syntax to this also. You should look it up. I think if you search, it will come up pretty quick.
Yeah.
Not
I
that.
think Python allows this kind of things in Pygame module or something. I don't remember the properly.
Oh, I see. Hmm. Yeah, I don't know. You just look it up. You should turn to Stack Exchange for this question. But yes, I think it's possible. I think in Julia also the scatter exists though. I mean, I don't have to mention the series step. It's just easier. Put to scatter instead of scatter. So, is that it? Yeah, I think that's it. Okay, let's begin. So to start with, we will need the position of the. We have the position of the anchor. We have like a 2D coordinate pair. It's like 1, 0 or something. And we need to get the coordinate pair of the ball. We only have the angle and the length. It is retrievable from this information, but we don't have it right now. And while plotting, it's easier if you have that beforehand. So I'll make a function like get position, define get function get position, and I'll take in my object, which is a pendulum, and maybe the nth time step. So an int 64 tells me which time step I want to get the position from. So it directly takes the trajectory and then it gives you the position at that point of the trajectory or something like that. So does anyone know what expression it would be? To get the x comma y pair from theta and L basically. It's pretty simple. You have to draw it out, I guess.
L sin theta and cos theta.
What I'm sorry, I didn't hear you.
Now is it like L sin theta and cos theta?
Right, right. And that will just be offset by the anchor points. So what is written is tuple or a list of points, wherein the first, a tuple of coordinates. So it's a single point. It's just a single point. Wherein the first coordinate is the x coordinate, which will be given by the object dot anchor. I'll access the first object. So this is like accessing the first element of an array. So I change it to the second element of the array and so on. So I take the x coordinate of the anchor and then I add object dot length multiplied by sine theta of sine of the angle, right? The angle is given by object dot trajectory at the nth time step. So this gives you the angle at the nth time step. I've taken it and put it. Is it sine or cos for x? feel like it should be fast. Right. So a similar thing for y. Just put it here. This
So it will
actually,
be sine only. Depends on how you're taking the angle. So
my angle is
you're taking
this
the angle
function is
from
vertical.
the, yeah. So then it will be
On the vertical
sine
will
theta
be
for the x and cos theta.
So
theta for
for
x.
x it will be sine, right? But this coordinate will change too. So it's the y coordinate of the anchor. But also I think I should add a minus sign somewhere because y will be cosine. Right. So the y coordinate will actually be negative. I think this should be right. We'll see. But basically, also this syntax doesn't matter. Okay, it doesn't care about the spaces and stuff here. It just looks easier for the eye. So I'm just saying the first element is the first coordinate and it's separated by a comma and the second coordinate here. So if I say suppose get position of my object at the time step 5, it will give me a pair of values, which is presumably the x and y coordinate of the ball, right? So one problem is solved. What else do we need? Hmm. I guess now we just have to try and plot the pendulum. So let's say function display, maybe display or get frame or something like that. But we'll see what to do. So I take the object pendulum and then I take which frame I want to display, which time step I want to display. And now I start with the position. So I'll define x and y to be the get position of the object at time step n. Okay. So this assignment, I hope it's this one, just since get position gives a list of two values. If I write x comma y equals this assignment actually unpacks both of the things. So this one gives like a list of values, right? 1 and 0 maybe. It just assigns x to 1 and y to 0. So it's convenient way to do that. But specifically the number of arguments here should be equal to, well, not strictly, but uh, hmm, should I? Okay, let's just say that the number of arguments that this is returning should be equal to this, but not necessarily. It should be greater than or equal to, I think. Should not be lesser than that. That will cause a problem, right? Yeah. So the number of arguments which this is, like returning back, and if I give like a z here, I think it'll be problematic because let's try display of object at 5. Right. So you see what's happening because it's not giving those many values. So on the other case, if I just put x, it's fine. It'll just give the entire list to x. So when you're using the syntax, you just have to be a little careful about that. Okay, so we have the x and y coordinates of the pendulum bob. So now we've got to draw some kind of a circle around that point, right? So this point, this position is somewhat like the center of the bob, and we have a radius also for it. And we would like to draw a circle. So let us define like a helper function. We'll say circle. I need the coordinates of the circle to plot it. I just showed you how plotting works, right? I have to give you like a list of x coordinates, a list of y coordinates, and then it plots that. Well, that is one way to do it, but that's the way we'll be following. So in that case, I'll need like a list of x coordinate lying on a circle and the corresponding list of y coordinates. Does anyone have an idea of uh, easily generating such a list? So basically, I want to plot a circle. How would you do that?
So you could take like any random theta values between 0 to 2 pi and just go cosine and sine.
Right, exactly. So what I will do here is I will pass two arguments. This is the h comma k is like the center coordinate of the circle, and I'll need a radius. So that completely specifies what circle I want to plot.
Can't you take a vector for hk? Wouldn't that be a better thing to do?
Yeah, sure, I can do that too. So I can just say center with a vector of looks 64. And more specifically, it's a vector of two entries only. It doesn't know that Julia doesn't know. I could pass more entries as well, but we know that we want to utilize it only for two, because two dimensions. Right. So we have a center and an R. What do we want to do now? We will generate a range of thetas as you told. So I'll write theta equals range starting from 0, stopping at 2 pi with a length of maybe 50 points. 50 points should make somewhat a smooth circle, I think. So now we have a range of theta. So let's see what this range actually returns. Okay. So range returns some weird object again, like we saw yesterday, separated by two colons. This is basically a start, the step size, and where it ends. So this is like 2 pi, 6.28. So if I collect this, I'll get the actual list of values. So yeah, these are all the values which it goes over. So this is a list, and I want to basically apply what would be the points on the circle now. It would be something like center of 1, which is the x coordinate of the center, plus the radius times sine of theta. And the second would be center of 2 plus, which is the y coordinate of the center, plus r times cosine of theta, right? Except I have to run this.
You messed up the sign in.
Or is it swapped? Is that fine?
Yeah.
Okay.
Yeah, and like just small note that Julia indexes from 1 instead of 0, unlike other languages. It's just a thing to remember.
Yeah. Okay. So these are basically the sets of points I want. But the thing is, theta isn't a single value, right? Theta is actually a range of values. So I want to run this function over an entire range of values. So which is basically over the entire array. So let's see how we could do that. For example, if I do cosine of 0.5, it gives me some result. If I pass it a array 0.5 and 0.6 maybe, does it work? No, it doesn't, because cosine doesn't know how to behave when I pass it over an entire array or a vector. So in that case, what do I do? There are many ways. I could, maybe the first thing which strikes to you is writing a for loop, right? I can write something like for element in this list, just print what sign of element. So this way it will loop over all the elements in this, and then it would well, not print, maybe you would append it to a list, but something you do here, you compute it, right? So you will loop over the entire list. But there is a nicer way in Julia. So there is something called broadcasting. Namely, it allows you to do many things, but in our context here, what we'll see is, if I have pause and we tried this, right? This doesn't work. It says no, I can't do that. So in this case, what we do is we just put a dot in front here, okay, between the function and the parenthesis, which is having the arguments of the function. We do that. Just look, it worked. And what it's basically done is it's made a new list wherein the first element is cosine of 0.5 and the second element is cosine of 0.6. I could have as many elements as I want here, and it would be able to do it. So this dot, right, it is actually a shorthand for an operation which Julia is doing called broadcasting. Okay. And for our purposes here, equivalently, we can consider broadcasting as simply uh, performing the same function element-wise over a given list. But it can do something much more also. And it doesn't end here also. I can broadcast in many different ways. For example, 0.5, 0.7 plus 0.7, 0.8 maybe. It could actually work as it is, I guess. Maybe that's not good enough. Maybe 0.1 plus, right? If I try to do this doesn't make much sense, right? I'm trying to add a scalar to a vector value. So it says, no, I don't know. I don't know what this means. So in that case, when I can use the broadcasting operator in a different way now. So here there's a binary operator, right? Which is the plus operator. In this case, I have to put the dot in front of it, okay? So what this does is it broadcasts this addition operation over this array. So essentially what this does is it brings both of these values. This is namely the scalar 0.1 and the vector here into a common dimension. So it kind of upgrades 0.1 into 0.1, 0.1, something like that. And now it can element wise add it, right? So if I do this, it just adds 0.1 to each entry. So essentially that's kind of what it does. And this will be really useful for us here, because what we want is now something like the first list will be, let's say, I'll just remove this. Let's just deal with the x coordinates. I'll say x coordinates equals center of 1 is what? It is a uh, it's a single number, right? This is basically the x coordinate of the center. And I have a radius which is also a scalar value, and cosine which is a function which takes a scalar value, except theta is actually a range which is an array of values. So firstly I'll put a dot here, okay? So this broadcasts the function over theta. That means it applies cosine over every element of theta and returns an array again. So this highlighted thing is another array. But now there is a scalar multiplication. So again I put a dot here. Now it knows that, okay, I'll take the scalar and multiply element wise to every element of this resultant array. As a result, this highlighted part will again be another array, right? Which has been element wise multiplied by r. So I'll put another plus here because this is, I'm sorry, another dot here. Because this is again a scalar value, which I'm telling, okay, element wise just added to the resultant array of this, okay? So as a result, if I just see what this gives, return x coordinates. And then maybe to circle center, what do I give? Center of 0 and 0, radius 1. Okay, what's the problem? I didn't close the list. Right. So it works exactly as we wanted. It gave a list of x values. So I hope that this I was able to explain what this does. Essentially, this dot is an operation which is called broadcasting. And for our purposes, we'll consider that it just does element-wise operations on an array using functions that otherwise only operate on like scalar values. Okay. So in a similar way, we can find the y coordinates also, except with this the other expression, using the y and sine theta. Yeah, it's broadcast over every operation, and fine. We got the x coordinates and y coordinates, and as plots would like it, we would like to give it back as a pair of values. So first a list of all x coordinates, and second a list of all y coordinates. Okay, and let's see, does it work? Nice. So it has given us two lists. The first list is a list of all the x values, and the second is the list of all y values. So that is one problem solved. We have just generated the points lying on a circle. So let's maybe just try and plot that. So let's start. Plot. I would like to plot the circle of center. What would be the center? The center is now x comma y, right? I guess, right. Okay, I'll leave this here because the get position gives you the center of the bob, and that would be the center of the circle we'd like to plot. So pass the center just like that, and then the radius we can access through object.radius because radius is one of the attributes here. So once you have passed that, the circle function should be working fine. Let's see, does it work? So let's display the pendulum, which is object, and at 5 maybe. Okay, it seems to work. It's plotted some circularish thing, but why is it elliptical? Can anyone say think of a reason why? Because what we generated here is a circle for sure. I know that. Yet what we see here is a ellipse.
The image is squished of sorts. I don't.
I'm sorry, I can't hear you.
Is the image squished? It's a circle, but it's like
Yep.
compromising on the
Basically,
face it has left.
so the term uh, this is called aspect ratio. That is the scaling of the y and the scaling of the x-axis are different. So in that case, I just set the aspect ratio to, I think 1. Will that work? No, doesn't like 1. Equal.
No, you put it in the wrong place. You have to put it in plot,
Oops.
not in display.
Sorry. Yes, yes. Display. Sorry. Aspect ratio equals 1. Okay, so now it's fixed. We have a nice circle. Let's just like make it nicer. Make it thicker. Give it some better color, maybe black. What else can we do? I think we can also do something like what is that? Series type, right? Series type, and make it a shape. In that case, it will fill a color inside. So I think we can also, but since this is like a closed figure, right? The points connect back to itself. So you can create a shape out of it. And can I set this to white? Nice. So see, you can't see the grid values, I mean the grid lines behind this because it's filled it with a color. And okay, fine. For now, we'll leave this. We'll leave it like so. And we have plotted the bob basically. What else is that? We would like to plot the anchor point as well, right? So where is the pendulum suspended from? Let's plot that. So that would be a very similar thing, except the center would simply be the object.anchor object, right? Object.anchor is already a vector of floats, which is like the coordinates of that. So I'll plot a small circle there, maybe with a radius divided by 5, a small circle, just so that it looks. Let's see, does that work? Okay, I'll just swap it up. I'll swap the colors so it's easier to differentiate. I'll just fill it with black. Okay, that's cool. But what happened to this plot, right? We had plotted two circles. There should be two circles now at ideally different locations, but we're only seeing one. So the thing is, uh, does anyone have an idea of what's happening?
You're not looking at where the other one's plotted. Either that or one of them is on top of the other.
No, no, that's not what's happening.
Okay, then I don't know.
Or I
So
didn't
like
understand what he said, but right, yeah,
first it plots the first plot function, and
okay,
then once it's done with that, it goes to the next one and plots it, and that's what we're seeing at the end.
right. So basically, what's happening is these two are being plotted on different canvas. So once this is plotted, it just chucks it out when I'm plotting this again. It just creates a new plot, a new canvas, and then plots it on that. So that's because uh, by default, whenever you execute a plot statement, you're probably plotting a new thing. So if you explicitly want to plot on the same canvas, you just put a plot bank. So it takes whatever previous canvas was and mutates that same canvas. So hence bank. So it should work now. Cool. We got an anchor point and we've got a pendulum. Nice. Maybe I'll make this smaller. Okay, that looks nice. So you don't actually have to pass aspect ratio multiple times. If we do it once, it's fine. So that's indicative of the fact that it's actually a bad idea to put it along with these properties, because you see line width, line color, and all of these are specific properties for this circle, but then aspect ratio is like a global thing for the entire canvas. So I can just put a plot band and pass just the aspect ratio alone. I'll just say for whatever plots you've done on this canvas, set the aspect ratio to 1. So this is more cleaner, right? Because here all the uh, specific attributes to this plot is seen, and this one is like a global property of the entire canvas. And similarly, I guess we can turn the legend off as well and false. Cool. So that's gone. And we can do some more nicer things. For example, we don't want the axis. So I'll put axis equals nothing. Nothing should work, I think. Nice. So the axes are gone. And then finally, we see like there are still two axes. Either remove that completely or maybe put like a box around it. So that is another plot attribute called frame style, I think. Frame style box, maybe. Nice. So that worked too. So we are getting closer to replicating what we want. So these things I know because I've already done this before once, but you should be able to find it on the documentation here. That is the entire list of all the stuff, right? That there are also like list of what values you can pass to it. These are the things you can pass to it, and so on. Okay, so we've done some things. One more thing, just for convenience, let's also take a vector of floats which tells me the axis limits, because otherwise every time the function, you see, this is like a weird, I didn't set the axis limits here, it just used its own. So every time, every frame, it will start shifting the entire axis. Maybe we should try that. Okay, that's actually fun to find. We'll add this limits later. Okay, so we've done this. The final last part of the plot is simply the line here, the line joining these two. So let's do that. The line joining those two simply consists of 2 points, right? The x coordinates will be the anchor, the x coordinate of the anchor, and the x coordinate of the bob. And the second list will be the y coordinate of the anchor and the y coordinate of the bob. Maybe line with 2, line color. Okay, what happened? I did not use plot back, so it overwrote or something. Right. Okay, so what's happening? Why is this coming above? Was this the first plot? Maybe I'll plot this after. This is one. Oh, right.
You have to change the.
Plot panels are right now. It's fine. So like the order of plotting, right? That comes it forms like layers on top. So plot this last, so it comes on top of everything. Okay, so we have plotted our pendulum basically. We'll make this thicker. Right? There's a comment. Commenting is good. Not commented anything. I commented just this. But generally, when you make the functions, it's good to make the functions itself very indicative of what you want to do with them. So in that case, comments actually become redundant in some cases. So that's actually nicer, because you just look at the code and then you know exactly what it's meant to do. Okay, so this one is plotting the line connecting string. This one is plotting the uh, plotting the. Okay, so we are done basically, right? We are done with this. Cool. So we have written a function which now takes an object and displays the pendulum at some specific time step. Nice. Let's just throw this away for a while. Now we get to the fun part. Okay, the interactive part of Pluto. So that's why I asked you to install Pluto UI also. Let's see what we can do. Because here I can change the values, and then okay, sure, it does something, but that's not fun. Let's um, make it more interactive. To begin with, let's first simulate our object for longer time steps. So let's take this. Okay, so I have an object. Okay, I will make a d here, which is like maybe 0.01 should be fine. Number of steps, which maybe 500 should be fine. So I'll just replace these here. It's just easier to change it when they're all in a single place. Okay, so we have done this. So at the end of it, I will have this object with trajectory. Let's see. Does the trajectory have 500 points? Yes, it does. Okay, we are good. So let's see. Now, okay, I want to, I've been displaying it like display object at some frame, right? So what I want to do is change this frame with some kind of a slider, okay? So Pluto UI gives a very convenient way to do this. The syntax for that is basically at bind and then some variable to indicate the frame. Maybe I'll say frame number, okay? And I'll say slider and give it a range of values. So what range does this work from? I know that there are only 1 to n steps because there are only n steps, right? So I only have 500 frames in here after the evaluation. So I give the slider from 1 to n steps. Does this work? Nice. So it just created a slider for us. And what it does basically is frame number is a new variable we've created here. And when I change the slider, the value of frame number itself changes. So that's like really convenient, right? It's an interactive thing. You can also use your keyboard, like arrow keys also. So at bind, what do you see here? I've just introduced yet another thing in Julia. What this is called, whenever it's prefixed by an at, this object is known as a macro. So what a macro does, you should probably look that up. I myself don't know much about it, but it's there somewhere in the documentation. But it makes things convenient. Okay, that's all you need to know for now. And somehow this works. It makes a slider for us, and we are good. So now all we have to do here is the frame number here. And since Pluto is reactive, right? That means it knows when I've changed the frame number by changing it here. It will automatically update my plot here. So now I just go through this. So it's actually plotting it. And the plots are fast enough that as I'm changing the values of frame, it's actually able to plot it in essentially what is real time. So that's pretty cool. But the thing is, since we've not set the access limits, right? Every time the access limits are actually changing, that leads to some kind of weird uh, simulation. It doesn't look like a pendulum oscillating. It looks like everything's just oscillating, right? Both the anchor point is also right. So let's just fix the limits. We'll pass another variable as a display function here. I'll say, okay, I'll also pass some limits. It's a vector of float, and I will set the limits here. I'll say x limits are the first two limits, just limits 1, 2. Okay, I guess we've not covered this, but if you've done Python, then if you have a list like this, an array like this, I can access x1 as like so, x2, x3, and all. I can also access a range of values. If I write x of 1 to 3, this range is just the unit range which we talked about. So it just gives 1, 2, and 3. The only difference is that in Python, this last value wouldn't come. The last value is exclusive or something like that. But otherwise, it's the same thing. You just give a range of indices and it gives you the range of values. And then, yeah. So I'll use that here. I'll say take the first and the second one to be the x limits and the uh, third and fourth value to be the y limits. So we should be good. Right, this is giving me an error now because I've not passed any limits. So let's say the pendulum is of length 1, right? What length did we give? Length is 1. So I'll put a minus 1.2 to 1.2 and 1.2 to minus 0.2. I think that should work. 0. This is the y limit. So y limit from this to 0.0. That should work, I think. Okay, that kind of works. Could be better though. So maybe this is high, way too high. What are we changing? Okay, fine. I'll just stick with this. And this maybe not 1 maybe. Okay, this looks decent enough. Maybe this should be actually lower, I guess. Should be maybe 0.1. Fine, fine, fine. I'll just stick with this. This should be enough for us. Maybe this is also a bit too much. Okay, so let's try now. I've fixed the access limit. So now it looks like a pendulum, right? And if I plot it, well, it looks a bit slow. So let's put a step here. Let's say, okay, only allow the slider to skip in steps of 5. So I don't want the in-between frames. So maybe that's a bit too choppy now. Just put 2. Yeah, that looks nicer. Somewhat better, I guess. Yeah, so essentially we have simulated our pendulum. There is a nicer way though. Here I'm manually controlling it, right? I'm like telling it which frame to go through. There is another macro called at GIF where I can loop through every frame. So I can write something like at GIF or or maybe like frame in range again 1 to n steps maybe, and then end this. And inside I can say every loop I want you to display something and add that to a GIF which you're constructing. So I'll say, okay, just display the object. I mean this same thing. Just use frame here. Use this index from the loop instead, okay? And we know that the result of display is actually a plot. So it will take, and this is like the only line inside this block, right? So it will take whatever this statement has evaluated, and then it will start constructing a GIF using that. So let's see if that works. It will take a little while though because it has to plot all of these at once. So I like using the slider better because essentially it's real-time plotting. It doesn't plot the next frame until you asked for it. So you don't have to wait. This takes a bit of time though. You can also adjust like frame rates and stuff. And yeah, there you go. You have a simulation of a pendulum. Or we will stare at it for a while and feel happy. Okay, so any questions maybe? There is more we can do from here. Actually, I don't want to do it now because it's already 4, and also I've already subjected you guys to enough following me coding along. But the thing is, what you can do is, instead of having a single pendulum object, have a list of pendulum objects and somehow display all of them on the same plot. So that way, if you've seen the GF which I sent, which Sahil sent in the email, that's how I created that. Somehow I plotted everything on the same thing. You'll have to create a different display function actually, but I'll not tell you too much in detail. So you can plot multiple pendulums and then see whether how they behave, right? Because if you take the small angle approximation, the time periods is actually independent of the amplitude, right? Whereas here we've not done such an approximation at all. We just as get alpha. Yeah, sure. So here we've used sine of theta, not theta. So we actually implemented the exact model. In some sense of the word, it's not exact because there are still numerical errors. But this actually displays that the time period is in fact dependent on the amplitude. And if we plot many pendulum, that will become apparent. And besides this, I think someone else suggested at the start of the session, I guess, you can remove this trajectory altogether and make the theta and omega itself as trajectory, and then plot like phase space plots and all. Now that's more like a physics of it, right? So you'll see something like the small angle approximation would give like a perfectly elliptical space, whereas this would give some more of a deformed thing. I've actually plotted that. Like let me show you. I will also flex a bit about another project I did a while back. Right, so we basically I think like last summer also, some of us made like a website to host interactive simulations. So it's essentially the same thing going on under here, but except it's way cooler because it's actually interactive. I can click where I want to drop the bob and then it does it. So here I've plotted like kinetic energy of system and phase space. If you see, the phase space is not perfectly elliptical as you'd expect. It's starting to deform as I go to larger angles. And kinetic energy, it's no longer a sinusoidal wave, it's rather some weird deformed shape. This also has become like an line. But yeah, so if I make a small angle though, this looks like an ellipse and this looks, somewhat like a sinusoid. So that's kind of cool. So in the limit of a small angle, our results were correct, it looks like. So yeah, you can explore lots of things. I've not set up the apparatus to explore that by yourself, but it should be doable if you are able to follow what I was doing. With some minor adjustments, you can make stuff up here. So I guess with that, we will conclude our segment on the simple pendulum.
Can we do it on Python?
Which can we do what?
Uh, these simulations on Python.
Yeah, sure, you can. But the only thing is last step now, making animating, visually like this, that will be a little bit more painful. Here it's like super easy syntax, right? Just quickly write it.
Yes.
That will have more lines of code, but in the end, you can get the very similar results. But the point is, in actual research level computational physics, you don't plot things like this. You don't visualize. You probably plot stuff like this, phase space and stuff like that. So for that, you just need static plots anyway. So Python is more than enough for that.
Okay.
Maybe we can.
Yeah, so I had a question. Not a question per se, but rather more of an assignment kind of thing for other people to explore. Right now, what we have done, and there's a reason why we have made so many functions. We could have just put all of this into a single one function which runs through everything, creates all the plots, puts out everything, right? And to explain and to see why it is necessary to make functions and not just write it in one loop in one line is try doing this. Right now, what we have done is very nicely, we have removed the get alpha out of the update function. So that allows you to, so the only the only thing that you can change in the entire physics of it is get alpha. The moment you change get alpha, all changes propagate. So if you go up to get alpha and then instead of using sine of theta, simply use theta. Don't use sine of theta, just use theta. So G into G by L, it should be G into L I feel, but whatever. Instead of sine theta, you just write theta. And then you will see that just by changing one point in one function, and this is the most simple change because you know exactly where to change, the changes propagate through the entire thing. So now similarly, let's say you have a damped oscillator where your alpha will be whatever that is, the g into sine theta minus beta times omega, let's say omega of the pendulum. So this is the alpha of that kind of pendulum. So simulate that as a homework or whatever. And that really shows why it's necessary to write functions. Because then I can just test one thing. Let's say my code is not working. You test each function. If each function works, then definitely the code will work. If one function is not working, then I can isolate that the problem is in this function. That's the whole point of writing functions. You could have definitely just shoved this all into one thing, have no structures, have simply a list of omegas and a list of thetas which just keep updating and done. You don't even need this pendulum structure, you don't need any of this. But if I want to make a change, how easily can I make the change? That's what matters.
Right. So actually, maybe the simple pendulum is not the best example to go through that, but I deliberately use this kind of a structure because when you go to simulating maybe billiard balls or something, many balls colliding in some table or something, this kind of structure really helps there because there are many objects. There may be objects with slightly different properties, slightly different behaviors. In that case, if we separate out functions like so, I can utilize some other features of Julia as well to make the entire code more, like nicer to work with. So we introduce structure into our simulations basically. Because like Dhruva said, you could have kept all of these as just some variables in your code instead of packaging them into some kind of a pendulum. Uh, and all of these update, get alpha, evolve could have been a single function. So, but we've not done that. Maybe that will become apparent as you try other things also. So yeah, as he said, try like adding air resistance and also forced oscillations, and also maybe see if you can um, when there is both forced oscillations as well as damping, you should be able to see some kind of a resonance also if you plot the things properly. But maybe those are some things you can explore, like in the physics side of this. But yeah, I guess that's it for this session.
I had a question. So
Yes.
we can't use the sign inbuilt sign function on vectors, right? So how would you do that if I want to apply sign to a function to a vector
Are you asking in Julia or like in general?
in Julia? In Julia,
We just did that now.
You just put a dot in front of it, it broadcasts to everything.
Right.
right? Okay.
Not just for cosine also. It can work for anything. If I rate x equals x square, and then I have x as a list of values. Then I say f dot on x. Okay, maybe I should name this something else. I'll name this array. F dot. It applies it elementary.
Right. Yeah.
So it doesn't have to be signed, but any function is fine.
Right. Right. Okay.
Broadcasting works farther than this also. I've not displayed all of its capabilities, but one nice use case is this. I've also like chained multiple operations, right? That's also fine. Yeah. So one thing we didn't discuss, we just randomly set a delta t here. That this actually has implications for the error accumulated. There are like concepts of stability and like accuracy of your solutions. Uh, so there are things to go through this because I don't know if my simulation how good is my simulation. I just made a very rough estimate that the errors are accumulating as delta t square, I think. But that's not enough. What does that tell me? So there are better ways, and in this case, simple pendulum being such a simple system actually is fairly stable under like smaller delta t values also. I mean, like relatively larger delta t values also. There are other systems which like absolutely will not have that. If you make like 0.05 and all, it'll give like really really bad results. Like you'll have a pendulum going like this, and then it'll suddenly shoot off to infinity or some shit like that. But so it's very dependent on the differential equation you're actually solving. So there are different classes of differential equations, and this method, no, this way of updating time steps, this is called the Euler method. This is called the forward Euler method. Forward. And this is like quite literally the most simple way to do this, like approximating derivatives. There are like a host of so many other methods, catering to specific differential equations. So in those cases, yeah, maybe I will try to figure out an example where Euler method fails horribly. So in that case, we'll be. I think the double pendulum itself.
I mean, even this, so the Euler method will fail in the sense that if you look at energy conservation, it won't
Right,
conserve it
right, exactly.
properly.
But the drift is not that large that, if you run it for like 500 times, if you'll probably not notice much. But
Yeah.
that is a drift. It slowly goes away. There are solutions though which don't drift. It quite literally just shoots off. Those things are, like unstable. In certain regimes of delta t values, it's a bad algorithm. It does not even give you an approximate solution. It just gives you some random behavior. So
Yeah.
that's where, like the field of numerical analysis really comes into play. You need to know when your algorithm is going to work, or else you're just throwing some random thing and hoping it will work. Although that's going to be a common theme in what we'll be doing. So generally not a good idea. So yeah, I think in the double pendulum, maybe Alhad will take that one. I'm not sure. In that case, the forward Euler will very clearly show deviations from energy conservation. It's like suddenly you'll see as if the pendulum system is gaining energy from somewhere, when really that's not physical. So in that case, we'll use something called an RK4 algorithm. So yeah, so that's just something to look forward to in future sessions.
Wait, but like, will Alhad sit and like implement RK4 or will he just use diffq.jl?
So I'm not sure what he'll do. I'm not even sure if he'll do it. He said he would rather prefer it if it was offline, and I'm not sure how viable that is. So right, we'll have to see. I mean, do we want to implement RK4? I don't know. It's kind of boring, but
Yeah,
we'll have
that's what I was
to do it
saying.
at least. Just see what it does. But
Yeah.
yeah, Euler method is just too easy to implement. So we just. I think the next session could be maybe on the billiard balls. That's a chaotic system. We can observe chaos there also.
Yeah,
And
billiard balls would be fun, yes.
mm, let's see. It depends because I don't think I'll have time to take the next one also. Maybe Dhruva can take it. I'm not sure, but someone else.
Well, there is already one on the solar system.
Right, that is
I
one.
mean,
Dhruva
so
has already
that is
pre-recorded it also.
definitely not chaotic, but I mean, it's not chaotic for two systems, but at least I mean, like you can look at it and you're like, huh, okay, this makes sense.
Right,
Because
right,
it's all smooth stuff. The problem with billiard balls is that you have to see if they are colliding and stuff. So
right, right. So that adds a extra layer of complexity.
yeah,
But that makes
but yeah, definitely.
huh.
If you guys are interested, then definitely go through the solar system thing.
Right.
That
See
should
this
be on the
link in the
resources page.
Paratha page. I'll send that in the Discord group also.
Yeah.
Hmm.
And there also I have made sure to use the planet structure because there definitely you need structures. There you can't do this. I mean, you still can, but like
It
there
looks
it's
easy.
really shiny. Why you need good structures.
Right. Okay. So I guess that's it. Unless anyone has any other questions. What would be good is if you guys can implement or change things, explore it by yourself and put it on the Discord group. No, it'll feel as if, I'll know for certain that you guys have actually been following and learning something. And it'll also initiate some discussions within ourselves. So I would encourage you guys to do that if you have time.
Like I can give a recommendation of what to try after the simple pendulum. You can try the what do you say, the cyclotron system. So like if you have a given electric field, magnetic field, and initial velocity, how would the charged particle move? It's a very fun system to model. Maybe you guys can try that. And you have to use the same Euler integration only. So maybe you guys can try that.
Right. Maybe we'll make a list of suggestions we have and just put it in the channel so you guys can try
Yeah.
whatever you like. Okay.
So
So,
if there are no other questions, I'll end the meeting.
yep, sounds good. Thank you guys for attending on a Sunday.
One second. One sec. Sahil, I
Yeah.
think you wanted to do quantum computation kind of thing, right?
Yeah, but I can do the coding part. I'm not sure if I can explain the theory part as well as I would like to.
Oh, I was hoping that you do the explanation and I do the coding. But okay, in case you want me to explain it, that also is fine.
Hmm.
But then
Right.
that will definitely be only MS. I mean, the second years onwards. So that is MS 20 onwards. Because the
Yeah, yeah.
first years will not. I can't explain quantum mechanics. I mean, I can explain quantum mechanics, but then we'll never end.
They
We'll have
haven't
to
done
start
linear
with,
algebra
okay,
also,
start here,
so
we function. We
yeah,
can't do that.
yeah. That's fair.
Yeah.
Could you send the talk that you gave to MS-19? Could you send that? I wanna like get an
No,
idea
no,
of
that was
what level.
2019. That was long time ago. That was when everything was offline, so we don't have it recorded.
Acha. Oh wait, yeah, no, right. Okay, okay, fine. I'll message on Discord to see how to proceed.
Because I think that is our next logical step from here. I mean, it is a pretty big jump, but it seems like something which diversifies without getting too in depth about
Yeah,
just classical numerical computations. Because then you can show a little bit of symbolic manipulations and stuff like that, which is nice.
yeah,
Plus, also do some physics.
and it is more pop size, so people will be excited.
Yeah, it's all very interesting for people, and everyone like,
Yeah,
oh, can't compute.
right.
Okay, sure, sure.
Okay, okay,
Bye
guys.
bye.
If you have no other questions, I'll end the meeting. We'll
Yeah.
share
Bye
the
bye.
recording. So, bye, guys.
Oh, thanks, Akshay.
Yeah, thanks for